short quiz from the morning session. So when can you not use visualization? Give a scenario use case where visualization is not good.
When we know exactly what we want to search for.
Yeah, so if you know what you exactly want, then maybe searching or other methods would be better. Okay. So give two criteria for good node link layout which are conflicting each other.
Nodes should have equal length edges and there should be no crossovers.
Okay, good. Okay. So in force directed layout, so what is generally the repulsive force? So what does it model?
Two vertices repel each other if they're not connected by an edge.
Yeah. And why do you need that? Yeah. So that nodes that are not connected should not be close to each other. Okay. So what is a disadvantage of matrix based layout?
You cannot show direction graphs through. Look, it's like when A to E is going, for example. If you mark it in matrix, you cannot tell if it's A to E or E to A.
Yeah. For topology based task, yeah.
You can't visualize paths.
Yeah, you can't visualize paths. Yeah. Okay. So what is the purpose of dimensionality reduction? Why do you need that? So that because things in low dimension looks easier to understand and visualize. So as with other areas, so machine learning has been getting used for graph layout. So what some people have done, they have taken a lot of good visualize layout, and then you have used machine learning to try to understand exactly what is a good layout, and then if a new graph comes, then they will try to use that. So you learn from examples and create a machine learning model, and then you try to create a good visualization for that. Okay. So I think later in this course you will learn about graph neural network. So graph neural network, what it does is given a graph. They will try to create a embedding of that graph. So for example, they will try to create a computation graph. So they will put these nodes in a two-dimensional space, and the how we will put in this two-dimensional space if nodes are close together in this graph, they will be close in the two-dimensional space, and how the nodes are close together in this two-dimensional space, that can be determined by various criteria like how many edges they have, how many nodes they have, and so on. So what people have done in this is utilize this graph neural network to come up with visualization. So they try to copy the graph into the GNN's space and then try to utilize that for visualization. So this is deep GD. So what they do is they use a graph neural network to position the nodes so that the desired aesthetic metrics are optimized in the resultant layout. So you will have the 2D layout, and in that 2D layout, the desired aesthetic metrics will be utilized. And so based on that, what you can do is you can create this kind of graph neural structure, and then based on that you can do the visualization. And once you study about GNN, I think this would become more clearer. So another interesting approach to graph layout has been adversarial network. So adversarial network is another type of neural network that is becoming very popular these days. And this generative AI that is being done is based on this. So what happens in adversarial network? There are two kinds of uh, neural network. One is a generator. So the generator, what it tries to do is to generate something. So for example, so you see all these deep fakes and all those things happening. So generator will try to generate, so for example, images. And the discriminator, what it does, it tries to say that, okay, this image is a real image, this image is a fake image, and so on. So as the discriminator becomes good, so what it will become is that it will try to see that more and more. So generator will try to create more and more images which are actually fake, but the discriminator, if it cannot understand that, then what happens is that those fake images can be propagated. So they are playing an adversarial game. So what happens is the generator will try to generate fake images, while the discriminator will try to figure out that, okay, these are fake and these are real. So that is there in the context of, for example, deep fake, but so which is maybe not a good thing, but in the context of the graph layout, so you can have a similar kind of thing. So where based on training examples, the generator will try to generate some images, and the discriminator in this case, what it will do, it will take some ideal layout of that, and based on that they will try to improve the layout. And what happens by this is that more and more the generator will learn good graph layouts, and then if during the uh, testing phase, if some layout comes based on the model that it has learned, it will try to create a good layout. So more and more people are trying to use various kind of deep neural networks. So for example, graph neural network or generative adversarial network to try to create good visualizations for graph layout. Okay, and this is just emerging field. So for example, these kind of work has been done in the last 2 years only, and more work in this field will come up. Any questions? So, a lot of papers, if you have time, you can read. So, some of the work that we have talked about, starting from the first paper is a survey paper that talks about graph layout, two-dimensional graph layout. Then some of the important graph layout algorithms that we talked about, like Fruchterman and Reingold, Ifan, whose algorithm. And then we talk about attribute-based layout in this visual exploration of multivariate graphs. Node tricks, which is a combination of node visualization and link visualization. And the final one is a deep neural network based graph drawing framework. So next, let us look into trees. Okay, so a tree, as you all know, is a simpler structure than a graph. So it is a set of connected nodes. Our nodes have a parent and 0 or more children, and root is a node with no parent, and leaves have node with no children. So a tree is nothing but a graph with no cycle. So it's a simpler form of a graph. Okay. So each child can be treated as the root node of its own subtree. So therefore, the tree has a recursive structure. Okay. So each node, from each node you form another tree. Okay. And obviously there are a lot of practical example where trees are used. For example, network, file directory structure, organization charts, and so on. And you can have various tasks you want to do with trees, like describe, understand the structure, find items, what are the parent, children, sibling of X, where is this subtree, where are the nodes of a particular value located, what kind of attributes does this subtree have. So tree visualization has two kind of approaches. One is node and link and the other is space filling. So node and link, you have the root at the top and leaves at the bottom, is very common kind of structure for trees. Okay. Or you can have the root at the center and the T structure jutting out from the center. That is also possible. And sometimes that is a better way because then the space is more efficiently utilized. Okay. So just like tree is a recursive structure, you can have a recursive way of laying out a tree. You have a recursive algorithm where you first, when you are trying to lay out a root, you will say lay out the left child, then you lay out all the children and so on. And then that way the structure would be laid out from the bottom. So what you do is so height can be at separate level. Each level can have a height, and so repeatedly divide the space for subtrees by leaf count. So if a subtree has lot of nodes, then you will have more space for it. If a subtree has minimal number of nodes, you will have less space for it. So for example, this has only one node in the subtree. So for the second one, you will keep a very little space. Okay. So the problem that can happen with this is that as the fan out goes, then the real estate is very quickly filled up. So if there is lot of nodes, so that real estate will get filled up very quickly, and also if the tree is not balanced, if different subtrees have different number of children, then it would not be the space won't be efficiently utilized. So for example, there is lot of space if there are not children of some trees, subtrees. Okay, so that is another problem you have in this. So one algorithm that tries to avoid this problem is called the Rheingold-Tilford algorithm. So it uses a compact layout and uses symmetry. So it starts with the bottom-up pass of the tree. So you start with the bottom-up pass so that you know exactly how many children there are, how many subtrees there are, and so on. So y coordinate by depth, arbitrary starting x coordinate. So you merge the left and right subtrees and shift right as close as possible to the left. Okay. So you try to do this in an efficient way, and so the parent nodes are then centered above the children node. Okay. So once you have done the bottom up approach to figure out exactly where the children will put how many children different subtrees had, then you do the final top down pass for the assignment of the final position. Okay. So this is how this Rheingold-Tilford algorithm works, and for unless the number of children becomes very high, it works pretty well. Okay. So you can also add a third dimension into which the layout can go. So the benefit of that is that you can gain more space. Okay. So this is called the cone tree. So here the children are not laid out in a triangle two-dimensional structure, but in a three-dimensional cone kind of structure. Okay, and therefore you are utilizing the space more efficiently. You are using the third dimension also laid out, and the children of a node are laid out in a cylinder below the parents, and sibling lives in one of the 2D planes. Okay. And this is another view of the cone tree that can be seen. So cone tree, it is a more effective way to lay out trees and uses a smooth animation to help person track updates, and it is aesthetically pleasing. Okay. And so that disadvantage of a cone tree is that with 3D occlusion occurs. So if something is at the back, then you cannot see that. And 3D, of course, is not easy to implement and requires a lot of graphic horsepower. Another 3D visualization was it is like you lay out the 3D tree in kind of a landscape visualization, and you can move through those visualization. So if you had seen the movie Jurassic Park, that where the children were going into a room to manipulate the system, the two small child, so they were using a visualization like this. So this was done by SGI, which was a company which did a lot of good 3D visualization before it went bankrupt. Okay. So no, besides node and link, another kind of visualization for trees is the space filling approach. So in node and link, it's difficult to encode more variables for the node. So you can use the shape, color, and size, but all quickly clash with the basic node link structure. And so therefore there was another approach that was created which became very popular, where each item occupies an area and children are contained under the parent. Okay, so if you have a structure like this, so you see the root node has 3 children, so the overall space is broken up into 3 horizontal area. So you see the 3 areas are for the 3 children, and the amount of space you take is depending on the number of children you have. Okay, and then for the each children also, then they will now, the first you break it up horizontally, the next level you break it up vertically, and so on. So let us look into, and this approach was called tree map, and it was developed by Schneiderman and Johnson. Okay, so the children are drawn inside their parents, and alternatively you have horizontal and vertical slicing at each successive level. And you can also use things like color to represent some other attribute of the trees and nodes. Okay, so let us look at an example. So suppose we have a tree structure like this. So the top root node is 35. It has 3 children, 9, 26. So what you do is, and for this, for the sake of simplicity, these numbers represent the number of children each node has. Okay, but it may not be the case. So because the first node has 9, so we have broken up this overall space for 9, then 20 and 6. Okay, the overall space has been broken up horizontally, 9, 20 and 6, based on the number of sub children it has. Okay, and so the next level, what you do, first level you had broken up horizontally, next level you break it up vertically. So for 9, it has 3 children, 3, 1, 5. So you break it up like this. For 20, you break it up 7, 3, 4, 6. And the third, you break it up 2, 4. So each first level you had broken up horizontally, second you had broken up vertically, and now if you go one more round, it will be again broken up horizontally. So that is the kind of structure you will get finally. So you will break it. So here it shows a finance kind of stock visualization, where for the different sectors, so for example, stocks in the energy sector, stocks in the healthcare sector, so those are broken up, and then each of them layer individual stocks are again broken up. And here the red color is showing if the stock is uh, going down, and green color is showing if the stock is going up. So this kind of visualization is very good because it effectively captures the whole space. And also what you can do is you can use other kind of attributes like the red, the color, to give some other information about the hierarchy structure. Okay, so tree maps have been found to be a very good visualization for the data. Okay. Another example, so what they have done is news of different kind of areas, they have been broken up, and and you can see that the colors are using for different kinds of type of news, and the overall news space has been broken down. And so this is again a very good use of the space to show the whole tree structure. Okay. So how the tree map algorithm works is that you change the orientation from the parent. So once you start horizontal, next time you go vertical and so on. Read all the nodes at this level, make rectangle for each and scale to size, and the draw rectangles using appropriate size and color. And for each directory, so each, as you know, tree is a recursive structure. You again call for the for each of the subdirectories. So this is the way that tree map works. So try to draw a tree map for this structure. Okay, so there are various kind of tree maps you can do. So you can have a non-nested tree map where you don't have borders, or you have a nested tree map, you can have borders. So everyone could do the tree map. Any problems?
How do you do the last child generator, which only has one?
So you can just have it as one. You don't have it for the others, but for just that one you can have it. You can create various ways, but that is one way to do that. Okay.
So like I put senior and junior in the same box.
Or you can just have one box for the junior, but nothing for the others. Yeah. You could do it. Any questions? So good representation of two attributes beyond node link. You can use the color and area effectively. You can use the color for some mapping. You can use the area for something. And but if you have a perfectly balanced tree where all things are looking the same, if you have say all nodes have the same number of children, this may not be a good thing, because then the visualization won't be able to distinguish based on color. Okay. And for showing the structure, you can supplement the tree map by changing the rectangles to other forms. So for example, you can have a cushion tree map. So what it, if you have some third dimensional data, you can use the cushion to show that. Okay, so you can have the show the structure of the hierarchy using the texture. Okay. So sometimes what happens is nodes with zero value may be also important. So some nodes does not have value, but they are still important. So for example, you are showing a tree map for your portfolio, and you have some stocks which you don't have, but you still want to show that in that tree map. So for that, you can have a context tree map where give zero valued items some constant proportion of the screen area. And so that is something you can do. So this is an example of that, showing the mutual fund portfolio, including funds not currently hold. Okay, so for things that you don't hold, you still give a small area to show stocks that you don't own. Okay. And another technique that has been used is the sunburst, which is kind of a tree map but in a radial layout. You start from the root at the center, and then you move out from the center to all the way across the graph. So this is called a sunburst visualization. And so here the color maps to file type of it. So this is a way of showing the hierarchy of a file structure. And you can have controls for moving deeper into the hierarchy, changing the root and things like that. Okay. So node link or space filling. So node link are typically better at exposing the structure, while space filling is good for focusing on one or two additional variables. Okay. But depending on the situation, you can use both. But tree maps have been also found to be very useful in a lot of scenarios. And these are some of the readings for the tree visualization. So far we have looked into static visualization. So we have looked into different ways of visualizing graphs. We have looked into different ways of visualizing trees. But the difference between, so this is, that would be similar to drawing a graph or a tree on a piece of paper. So the advantage that the computer brings is that you can now interact with the visualization in various ways. So one of the key ways we move beyond graph layout to graph visualization is interaction with the graph. Okay, so interaction is essential for understanding large graphs. Okay, so what is interaction? It's a communication between the user and the system, and a direct manipulation and instantaneous changes. So there is too much to be shown and many ways to show it. And so we use let the user dynamically control what he wants to see. Okay, so that is what is interaction. So we have seen this before. From the raw data, you have data tables from visual structures to views, and then the user can use various kind of interaction. They can change the data itself. So for example, they may do some filtering. They can change the mapping between the data tables and the visualization. For example, move from a tree layout, node and link layout to a tree map layout, or they can change the mapping. So we use different colors to represent different things and so on. Okay. So how it works is that you have the physical data which you present as a visual presentation, and so from the raw data you have the data transformation to get the process data. So for example, from the raw data you put it into Excel file to get process data, then you do some visual mapping. So for example, that I will use color to represent the age of the person or things like that. Then you have a visual presentation of that. So for example, you say I will try to do it in a graph layout. Then you render and get the actual view in the computer screen. And then from the computer screen, so from the data level, you have the visual level to the view level. So that is how you create the visualization. And once you have the visualization, then you can interact with the visualization. So you have the create a visual model of the data based on the visual data, and then you can do various kind of interaction to understand the data and get some various insights of the data and get the information that you want. Okay. And what are the kind of tasks that I will try to do with visualization? You can try to get an overview of that entire collection of data. You can zoom into part of the data that is of interest. You can filter out uninteresting items. You can get details on demand. So some part you want more details, you can get that. You can try to see relationship between items. You can get a history of the item, whatever you have done, and you can extract important information. So for example, if you have an overview of the data, from there you can zoom and filter to get some part of the data, and then you can zoom and filter further to get more about this data, and then you can get details on demand on. So this overview, view, zoom, and then details on demand, that is one interaction pipeline that people follow. Okay. And for this kind of interaction, you can use various kind of interaction techniques. Interaction techniques is the fusion of input and output, consisting of all software and hardware elements that provide a way for the user to accomplish a task. And the interaction techniques can be command line, it can be input based or direct manipulation based. And then, so there are various kind of interaction techniques that you can do. It can be selection, it can be rearrangement, it can be filtering techniques, it can be navigation techniques, and it can be multiple views. So let us look at this in the context of network visualization. So selection is just marking something as interesting. So for example, selecting a node in the graph. Okay. So rearrangement is changing the arrangement of the data. So for example, changing from node and link view to matrix representation. Okay. So provide a different perspective by changing the spatial arrangement of the representation. So for example, you have a graph. From there you can create a spanning tree of the data. Okay. So what is a spanning tree? for a graph?
Spanning tree, connected components with no cycles and having all the nodes located.
So it's a graph, it's a tree that you form by maybe a breadth first traversal of all the nodes in the graph. Okay. So you can generally, as we have seen, that tree understanding a tree is easier. So you can take a graph, you can do a form a spanning tree of that tree by, for example, removing cycles in the graph, as he said. And so this is a very common technique that you can do, and you can start that spanning tree from any root of the graph, and that's the way you can visualize. So, for example, 3 plus is a visualization that was done for a graph where you don't draw the entire graph. You have a focus vertex and then you incrementally expand and show connections, minimum span tree from there. So, for example, if you have a focus vertex, you take that and you show a spanning tree from that. So, instead of showing the whole graph in a node and link kind of layout, which is sometimes complex, you can create a tree kind of structure to show that. Okay, and you can have various kind of interaction. So a single click shows connections via highlight, and double click changes the focus vertex. Okay, so this is one visualization that was done, and my PhD was also on visualizing network structure using multiple tree structure based on various criteria. So that we have seen you can change the visualization from graph to tree, or for example from node and link view to tree map view and so on. So that is one interaction you can have. The other interaction you can have is filtering. So in filter, what you do, you change the set of data items so that you focus only on the kind type of data that you are interested in. So for example, given a graph structure, you can say only show me nodes of people in India. Okay, so then the whole large graph structure can be filtered to a smaller region. Okay. So suppose you have a graph structure and then you try to filter out some nodes, okay? And so how do you represent the graph after that? There are various ways to represent unselected nodes. You can first do ghosting. So in ghosting, what you do is de-emphasize or relegate nodes to the background. Or maybe you can show the nodes in a very light gray color, okay? So you can of course hide the nodes totally. The nodes that have been filtered out, you can hide them totally, or you can do ghosting where you just use them, show them with a very light color. Or you can group them. You can group them under some super node so that only that super node has all the unfiltered nodes. Okay, so that is one way of various ways of representing unselected nodes. So filtering is totally leaving out some data, while you can also have clustering. In clustering, you group data together so the data can be grouped based on various similarity measure, and the similarity can be structure based clustering or it can be content based clustering. Okay, in structure based clustering, what you do, you want to retain the structure of the graph. Okay, so you want to do the clustering while retaining the structure of the graph, and that is very useful because if you totally change the in content based clustering, you do it application specific, you do some clustering. So for example, you can be doing the content clustering based on people in different regions are clustered together. But because in the content based clustering you're doing it based on the various content, the graph structure will change. While in the structure based clustering, so there are various kind of clustering can be done based on the structure of the graph. So you may so for example, in the morning class you looked into various kind of techniques. So those kind of graph theoretic techniques can be used for clustering also. Okay. So what is the goal of clustering? You can find disjoint cluster, you can find overlapping clusters, and So one common technique is to least number of edges. So you can form cluster based on the least number of edges that are between the nearest neighbors. Okay. So one thing for doing clustering is that you can have a clustering in a hierarchical way. So you can start with a large graph and then you can use clustering to get a few nodes, and then you can do clustering to get smaller and smaller number of nodes. So we saw that during layout, graph layout also, this kind of clustering can be done, so that you can lay the graph out in a very high level with 50 nodes, and then you can go and try to do layout for those individual clusters. So clustering is a very useful method if you have a very large graph. So for example, you can from a 1,000 node graph, you can try to come down and form 50 nodes graph. Okay. So for example, if you have a graph like this, you can form a smaller graph and then you form smaller graphs. So you have clusters A form, clusters B, and clusters C. And then instead of representing all the nodes in those clusters, you can represent a meta node for A, meta node for B, and meta node for C. And those can be useful for visualization. We saw that it can be also utilized for graph layout. So you can, instead of laying out a 1,000 node graph, you can lay out, for example, a 10 node graph, and then inside of those clusters, then you can do another round of layout. Okay. So this is a good example of clustering. You have a 30,000 nodes, and from there you did some clustering to come to 750 nodes, and then you can come to 90 nodes. From there you came to 18 nodes. And now suppose looking into this cluster, if you are interested in one of those clusters, you can double click on it and see details of that cluster. Okay. So we have looked into circular layout before, and one of the problems of circular layout is that there are a lot of edges, because here the nodes are placed in the circumference of a circle, and the links are connecting all the nodes, and so the links become very difficult to understand. So therefore you can use a technique like edge bundling to understand it better. So what it does is bundles edge to and from similar nodes together. Okay. So for example, suppose you are interested only two nodes. Okay. You are interested only P0 and P4. So but they are not connected among each other. But what you can do from P0, it's to goes to P1 to P2 to P3 to P4. So then instead of showing all these 5 links, you can just draw one link from P0 to P4 to represent all these links. Okay. So in edge bundling, what happens, you identify which are the important nodes for you, and then instead of showing all the edges between all the nodes, between those two nodes, you only see the shortest path between those two nodes and show that edge. Okay, that way the number of edges that you are showing in a circular layout comes down a lot. Okay. So another thing that you can do for interaction is pan and zoom. Okay. So if you have a large visualization which does not fit in the screen, okay, so you can do pan and zoom so that you can get a better understanding of the overall structure. Okay, so geometric zoom is a simple blow up where you just blow up the data as you move further down, or you can have semantic zoom in, where the zooming is based on some content change. So for example, clusters. So if you have a cluster at a high level, you can, when you zoom, you can see the content of the cluster. Okay. So pan and zoom is of course used a lot in geographical mapping. So you have a map like this. You can see, for example, this is a map of Paris. You can zoom into part of Paris. You can zoom further. So what is the disadvantage of pan and zoom? So, so as you grow deep and deep, what happens is that you lose the context of where you are. Okay. So, for example, if I am new to Ahmedabad, if I look into the map of Ahmedabad, I start with a map at a high level. So, if I zoom further and further, I may not know exactly which part of Ahmedabad I am in. So, you have this problem of where I am, okay, based on this visualization. Okay. So objects may temporarily move away. So especially, so you are trying to focus on look at Ahmedabad and try to orient yourself based on the Narendra Modi Stadium. Okay, so you will say, okay, I'm on the south of the stadium or I'm in the east of the stadium. But if you zoom further and further, what happens? You may totally lose the stadium and then you are totally lost. Okay, so this is a big problem with pan and zoom. And to get over that problem, so one technique that have been used in visualization which has become very popular is called the focus plus context technique. Okay, so what focus plus context that is that you are focusing on some part of the data, but you also have context of the overall area. Okay, so you are not looking into the just the overall data, but you are also focusing on some part of the data. So that is what is focus plus context visualization. Okay. So, what is focus plus context? So, this is based on a concept called degree of interest. So, what it tries to do is that when you are trying to create a visualization, so the position of an item would be based on not only uh, its distance from the focus. So generally, what you do in in a generally pan and zoom is that as a if you are focusing on some part, things that are near that part you will show, things that are far away from that part you won't show. So the position of a node is only dependent on your distance from the focus area. But in a focus plus context, it is based not only on the distance but on the a priori importance. If something is of importance in this place, things that you are trying to see, we are also trying to give some importance to that thing. And so, for example, if I am showing a map of Ahmedabad, and we are focusing on maybe one locality. So we will show things in that locality in a bigger size, but also things that are a priori important. So, for example, the stadium is of importance to me. So we will still show it in a larger size. So the size of an item is dependent not only on the distance from the current focus, but also things that are prior importance to me. So, for example, if I am in Delhi, so I will show things not only that are in my current focus, things in the neighborhood, but also things like India Gate, Red Fort, which are landmarks of Delhi, so that people know where I am. Okay. So, this is the basic context of focus plus context, and for that, uh, and it is called fisheye distortion because it seems fishes, when they are underneath the sea, they are utilized, their eyesight are based on this kind of, they have both the focus and the context. So what you try to do, you pick focus points and map points within the radius using that. So the things that are near you will try to show, but things that are far away you will also try to show them, especially if they are important. Okay. So you can use the similar techniques for graphs. So you are focusing on this part, you are showing that, but things that are very far away, you are not totally removing that. You are still showing that them in some way. Okay. So that is called the fisheye views for graphs. Okay. So the problem with the fisheye view is that distortion should be also applied. So if you are going further away, you will still try to use distortion but show those nodes as well. Okay, and so therefore this what happens is that therefore the visualization at the end can become very expensive. So you can try to have other kind of visualizations for that as well. Okay, and one of the ways to show the overall structure is to use what is called a hyperbolic viewer. So, what we have generally studied is Euclidean geometry, right? So, what Euclidean geometry says that a straight line segment may be drawn from any given point to another. So, these are the postulates you studied in high school. A straight line may be extended to a fine line length. A circle may be described from with any given point as its center and any distance as its radius. All right angles are congruent, and if a straight line intersects two other straight lines and so makes two interior angles on one side, then the other straight line will meet at a point if extended far enough. Okay, so these are the Euclidean geometry, and so the final point is a parallel line postulate. Okay, it says that lines that are parallel never meet. Okay, uh, so, but then there are other kind of non-Euclidean geometry that is possible. One is so Euclidean geometry. The postulate is that parallel lines will never meet. But there are two other kinds of geometry which are non-Euclidean. One is elliptic, and the other is hyperbolic. Okay, and what we are interested is in the hyperbolic geometry. So what the hyperbolic geometry says that for any given point in line and a point P not on line in the plane connecting both the line and P, there are at least two distinct lines through P that do not intersect L. Okay, so what it means is that so they will uh, go further and further away from each other. Okay, and the thing for that is that in a hyperbolic geometry, so for a Euclidean geometry, if you have a circle of diameter 1, then the circumference is pi, while in a hyperbolic geometry, for a circle of diameter 1, the circumference is greater than pi. And how does it help us? Is that if you are now drawing instead of in elliptic plane, if you are drawing something in a um, hyperbolic plane, you have more space to draw nodes. Okay, so if you have in a Euclidean plane, you will have only about a pi kind of circumference to draw the nodes. In a hyperbolic geometry, you will have more space to draw the nodes. So if you take a hyperbolic geometry, at the end you will see that you have more space to draw the nodes like this. Okay, so you will have, so therefore the other approach people have used for drawing large hierarchies and large graph is using a hyperbolic browser. So a standalone 2D browser, 100 nodes can be shown, while in a hyperbolic browser, 1000 nodes can be shown easily because they have more circumference at the end. Okay, so what is the concept of hyperbolic browser? So natural magnification as a center. So layout depends on 2-3 generations from the center, and smooth animation, so you can change the focus and bring some other nodes in the focus. But so you are focusing here, but in the context you can see more and more nodes, so you can see more nodes in the context. So therefore you get a better understanding of a large tree. Okay, any questions? So you can start with one, so you can see the whole structure, you can see one node that is in the focus, you can bring that into the focus and see the structure change. So this is one way of showing the graph. Okay. So the problem, of course, is that it can be disorienting for the user as you change the focus. When a node is moved, the children don't keep their relative orientation. So now you are familiar in the Euclidean space, so you can see how the nodes will move. But in a non-symmetrical space like a hyperbolic space, this become a little problematic. The nodes lose focus for you. Okay. So you can do it instead of in a 2D plane, you can do it also in a 3D plane. So this is viewing graphs in the 3D hyperbolic space. Okay. So what they do is they take a spanning tree from the input graph and they lay it out in a 3 dimension. And in a 3 dimension hyperbola is a hemisphere. Okay. So a bottom up pass to estimate the radius needed for each hemisphere and a top down pass to place each child node on its parental hemisphere surface. Okay. Showing lesser surrounding the node of interest during the interactive browsing and fill in the details as the surrounding scene. So you start with the visualization, you can see, so you can see much more of the visualization utilizing this structure. Okay. So this focus plus context technique has been used a lot of time for doing various kind of visualizations. So for example, degree of interest is another approach which uses a fisheye like focus and context idea to draw a tree. So what it does is, suppose you are in this node of interest, so it will show it. So not only showing the node of interest, it will show its parental nodes till the root node, so that you know exactly where that node belongs, and it will show some of its sibling nodes, but the other nodes it would be grayed out. So that way you have a better understanding of exactly how that node fills in. Okay. So for example, display. So this is a uniform display of the nodes. So as you see, as you go down and down, the nodes are not totally disappearing, but are shown with very small size. Okay, but now if you bring this node 3 in focus, that node becomes bigger, but his parents also are shown and some of his siblings are shown. And now we have grown much further, so the node 203 is shown, but its parents, grandparents are shown, so that you know exactly how it is positioned, where it is shown. So this kind of focus plus context kind of visualization is a very good way of showing large graph structures. Okay. So there are three kinds of way a node can be shown. So you can, if for 70% you are doing a free layout, and then for some other parts and you are compressing the data, you are showing the nodes with a smaller size, and then for some other part you are just aggregating. So you are just showing maybe one node to show 10 nodes and so on. Okay. So space tree is another visualization which is similar. So that also uses this focus plus context. So here, so what they do, they show the parent, they show the child, and also for some parts that are not of interest to the user, they are showing it as a triangle. Okay, subtrees that are not of interest to you, you show it as a triangle where the size will indicate the depth and the shading indicates number of nodes inside the node. Okay. So this kind of focus plus context visualization has been utilized a lot to show large structures, which can be graphs or trees. And the final kind of interaction you can have is multiple views. Okay, so for example, you can have a matrix view in combination with the node and link view for various operations for gaining different perspective. Okay, so you can have both the matrix view as well as the node and link view. Okay. So for example, you can have or you can have multiple views. You can have a view of the graph and you can also have a list view showing details. So if the user is searching for something, they can see the node in the layout view, but also they can show the node in the link view. Okay. And so you can have graph structural analysis ranking with interactive visual exploration. So you can have a list as well as a layout of the graph. Okay. So you can have the graph visualization as well as a list visualization. So show both together. And and you can rank the nodes in the list view based on various social network attributes. So, for example, betweenness centrality, closeness centrality, some of the things that you have studied in the morning class: degree, power, centrality, hits, page rank, and so on. So, you know about hits and page rank? Yeah, okay. Okay, so and then you can show them, rank them based on that, and try to see the nodes in the, and nodes that are colored by red color in this view are also colored by red color. So the top nodes in this view are also highlighted in the graph visualization. Okay, and then you can see the graph view. You can, for example, take the highest node that is found for betweenness centrality and click on that node and get details of that node. Okay, so that way you can combine various kind of graph analytics with the visualization. So those are kind of interesting ways of showing the visualization. Okay, any questions? Okay. So I think now we will, after a break, we will show some Gephi tool which can be utilized, where some of the things that you have studied, you can see it in practice. Okay. Thanks.